When it comes to plotting trig functions, a lot of people are actually making this thing harder than it is already is. And they think that you have to know special angles, you have to know a bunch of things in order for you to plot these things. But that's actually not the case, especially if you really want to get a complete view of these functions and you want to analyze them and get a bigger picture of or the behavior of these functions without the use of a calculator. And most of the time, when you're using the calculator, you actually miss out some of the information that is contained within there. And once again, these questions are the one that I gave you as a homework. Please plot these functions without the use of a calculator. In other words, the reason we are saying without the use of a calculator is because when you're using radians, for instance, a radian is, you cannot really get to understand where is 3 over 7 pi radians. For instance, in this plot here, you find out that you can't really spot it where it is. But if you really try and plot this without the use of a calculator, at least you get to get some sense of, okay, this is how this shape comes about, this is how this comes about, and all that stuff. And again, what are the key things that I want you to look at when you're looking at basic functions? One, what is the shape of that function? Secondly, what is the domain? What is the range? And is it even or odd? And if it is even or is it odd, what are the properties that you can think of with that particular function? But one thing that I would like you to add here is that if you want to plot secant of x, I always say group it with cosine of x. And when you want to plot cosecant of x, I want you to always group it with sine of x. And that way you get a complete picture and a complete memory of how the shape looked like. And when it comes to tan of x, if you know how to draw this, always combine with that. And then in that case, you will actually know the shape of cot of x. But before we begin solving this problem, which I gave you as a homework, I want us to remind ourselves of a few things. We said that the origin here, we always mark it as O. I'm going to use a red O. And then if we want to plot with these functions, all of them, we said that, okay, it's fine. I want to pick a point somewhere on this circle here, and then you draw that you draw a line that is joining that point, and then after that you call that point B, and then the next thing is you also draw a perpendicular line that is moving from B to the horizontal axis. So this one here, we're gonna call it A, that point. And then the angle, which is the ratio of this arc length here, and actually the radius is the one that we actually call it our x. Now, take note that I haven't written anything there. It's because that this side is horizontal axis, and then this side we have vertical axis. Why am I not putting x and y there? It's because along the horizontal axis we always put the independent variable. The variable that we are allowing to keep changing, the one that we are controlling. So independent variables are the controllable variables. And then when it comes to this side here, the vertical axis is the output of these independent variables. So in this case here, you will find out that we keep changing the angle, and the angle is going like this. So the independent variable, which is x, is the one that is going like this. So there is no change that is happening along this horizontal axis, and there is not much changes that we can actually see when it comes to this x. So instead of that, we just decided that, okay, let's just put horizontal axis and vertical axis, and then later when we want to plot cosine of x or sine of x or sec of x or tan of x, we convert the information that is here such that the y-axis will be the output of these particular functions, and the x now, instead of changing like this, it is along the horizontal axis. So taking note that if we have this line and that line there, this is supposed to be 90 degrees. And looking into this angle here, we know that we can say something about sine of x. And sine of x, we know that it is the opposite side divided by the hypotenuse. And the opposite side here is the side that is opposite to the angle that we are changing there. So this angle here is opposite to that side, which means we're going to have our AB, and then divide by the hypotenuse of this right angle triangle, which is going to be OB. And then secondly, we said if you look into this, the cosine of x, which is the same as the adjacent over the hypotenuse, is going to be, adjacent is the side between the marked angle and 90 degrees, so it is this side, which is OA, divided by hypotenuse is OB. And then we do the same thing here for tan of x. Tan of x is the same as when it comes to sine of x, I can just say that this is just sine of x, and then you divide it by cosine of x. I know that you can use this, but let's just make it easy like this. It is just like that. And now we said that we draw our triangle, our circle here in such a way that the radius of that circle is 1. So going there is 1, the radius is 1, and the radius is 1. So in such a case, we know that OB, since it is a radius, so we know that this will be the same as AB divided by 1. So let me just write it here. We have our sine of x is equal to AB if we have a unit circle, and then our cosine of x is going to be the same as OA, and then the other curves you can find from here, because you know that cosecant of x is just equal to 1 over sine x. So of course, if you know these two, you know that cosecant of x is going to be 1 over AB, and then when it comes to cosine of x, sec of x is 1 over cos x, which is the same as 1 over OA. So this is the information that we actually get from this particular triangle. Now that we have that information here, I want us to take a look into this, copy it down, because this is what we need to plot that. In other words, we'll be plotting OA. What is happening to OA as we keep changing this x here? So we're going to plot OA like we did with AB. When we were plotting AB, we were actually plotting sine of x. And when it comes to that, we're going to use this cosine of x as input, and then we try to plot sec of x here. Now, let's look at the choice of AB so that we see where will our A be if we choose, where will our A be, where will our A be if we choose a different B. Now, let me use this color here. If I choose my B to be there, remember this is the origin. Again, we still have a unit circle, and the radius is equal to 1. And you draw a line there. Let me use this. You draw a line from B up to that point. We picked our B to be here. And then where will our A be? So you wanted to draw a line that is perpendicular to the horizontal axis, and that's where our A is going to be. So our A will be here. But if we choose a different B, that is B now is here, we draw a line. This is my B, new B, and then we draw a line to go there, and then let me do this. We draw a line from the origin up until B, and then after that we want to draw a perpendicular line to the axis, and then that's where our A is going to be. But if we choose a different B to be somewhere there, and then this is our B, this is our new B, and this is looking weird. This is our new B. Of course, you draw a line here to be this point here, and then you draw a perpendicular line to the horizontal axis, and of course this is perpendicular, and then that's where our A is going to be. I want you to take note that as we keep choosing B this side, A keeps moving to that side there. If I choose my B now to be there, let me use a different color, orange. I have my B there. This is going to be B, and then I choose, I draw a line from there to there. My A will be somewhere there. But now, if I choose my B to be at that point there, which is on the horizontal axis, let me use green here. My B to be there, and then this is my B at that point. What is going to happen now? You will notice that if I draw a line from the origin to B, and then the line drawn from B to A will actually make our A to be there. So my A and B are in the same point, because as you keep moving this side, A keeps moving that side, keep moving B, A keep moving that side, keep moving B, A keep moving that side. But when our B now is there along the x-axis, our A is at that particular point there. That's what I want you to take note of, that we have our A. When B is at that point, our A is at the same point there. So that's the first thing that I want you to note here. So now we have this, and let's go down. Now we want to actually plot now cosine of x, A cosine of x, which is the same as OA. So again, we had this nice figure here, and then we said this figure is this side. We have a vertical axis, this side we have horizontal axis. And of course, as we said, that because we want the changing variable to be along the axis, and then the one we're controlling to be along the x-axis, and the one that is the output to be along the y-axis. So we are changing information that can be contained there to this one over here. Now that we have that, I want us to take a note of few things so that we can a little bit revise at what is going on there, so that we can continue. Last time when we were dealing with the radians, if you still don't understand radians, please check that lesson there. We said that here is 0 degrees. So let me try and draw a circle here. It's not gonna be perfect. This is bad. It's not like it's not perfect, this one, it is just bad. This one also is not looking good. This one also is not good. What's going on here? Let me try and have this one is better. Now that we have this, we said that here we have an origin, and then here we want to have a 1, and there we have something. If let's say now I have 0 degrees, 0 degrees is there, and then I can open my X to pass through this point. Let's say it passes through here, or X passing through there. Let me plot this. So if I say my x now is gonna be here, so if my x is at 45 degrees, it's gonna be somewhere there, and then if x is 90 degrees, it is there, and then 120 somewhere there, and then 180 degrees, and so forth, the 270, and then our 360 there. We said that these are in degrees, and we want to convert them to radians. One thing that you have to note of is that 360 is the same as 2 pi radians. So 180 is half of 360. So in order to convert 180 degrees, I just take half of 2 pi, so it's going to be pi radians here, and then half of 180 is 90, which means half of this pi is going to give us this angle here. Half of 90 degrees is 45, so half of this is going to be 45 here, so this is supposed to be pi over 4. So here we have pi over 4, and then pi over 4 times 2 is that, and then pi over 4 times 3 is this angle here, 3 pi over 4, and then pi over 4 times 4 is going to be pi, and then pi over 4 times 5, this one is going to be 5 pi over 4, and then 6 times pi over 4 is going to be 6 pi over 4, and the common factor here and there is 2, so 2 goes 3 times, here it goes 2 times, so 270 is going to be 3 pi over 2, and then 7 times pi over 4, this is going to be 7 pi over 4, and then here we have a 2 pi. So now if we wanted to find these angles here, instead of having here the angle, the degrees, we can use these radians here. So here we will end up having pi over 4, and then here pi over 2, and then here 3 pi over 4, and then here pi, and then here 5 pi over 4, and then here 3 pi over 2, and then here 7 pi over 4, and then here we end up having our 2 pi. And then this side, this is 0. This side we just have the negative of these numbers, so you're going to have negative pi over 4, and then this side you're going to have negative pi over 2, and then this side here you're going to have negative 3 pi over 4, and then this side I will have negative pi, and then here I will have negative 5 pi over 4, and then here I will have negative 3 pi over 2, and then here I will have negative 7 pi over 4, and here I will have negative 2 pi. And of course we can continue that way. That's what this arrow is all about, that way and that way. Here I want us to have a 1, and here I want to have a negative 1. The goal is very simple. We want to plot cosine of x, which is the same as OA. Okay, let me change this now. And also another thing that I wanted to do, I wanted to plot, to have a line that is gonna pass at 1 there, and then I want to have another line that is going to pass through it, -1, and then after that I wanted to have, let me use a white there, I want to make these dotted lines because this is just the and then let me try and make dotted lines here, and then here I'm also making dotted lines. So these are just the dotted lines just to say the upper bound is 1. Now let me go back to our original color, which is blue. Let's come here and analyze what's going to happen. If my origin is okay, if my O is at the origin there and x is equal to 0 degrees. In other words, x is still there. I choose my B to be that point. We said that our A will still be there. So, and this radius is equal to 1. The length of OA. What is the length of OA? You will find out the length from moving A up to that point here is the same as just a 1. So when x is equal to 0, which means the angle is equal to 0, B and A are in the same point, but the length of O to A is 1. So we are somewhere there. When x, remember that we pick our B now to be there, and then we move like this, such that this point here is 45 degrees or pi over 4 radians. So this is our new B. Let me use a different color there. So we're going to have that. This is our B. And then we draw a perpendicular line here such that this is going to be our A. If you notice at OA, remember that we want to find the length of OA. The length of OA is less than 1, so it is below this line there. The length of OA is still positive, is still bigger than 0. So it is still above 0. 0 is the horizontal axis or the x-axis. So when we are here, is somewhere there in the middle there. Of course, this is not drawn to scale, but if you notice this, at this point here, this length, if this one x is 45, this x is here, this is 45, this will be 45, because this sum of these angles have to add up to 180, and here you have a 1. So this will be an isosceles triangle. So this side and that side will have to be equal. So you can work something out and realize that will be somewhere there. And then now, if I choose our B to be here, so we have our B at this point there, our A now will be, because that point here, when you draw a line down to the line perpendicular from B to the axis, is going to form this angle here, 90 degrees. So our A is going to be at the origin, because the perpendicular line will have to come here. So our A will be at the origin. In other words, A and O are at the same point there. So the distance from A to O is just 0. So we are here. It is 0 because here we have pi over a 2. If I choose my B, let me use a different color there. If I choose my B to be there, this is B. You draw a line to the origin, and then you draw a perpendicular line to the axis. We're gonna get our A there. Looking at A, the distance from the length, the distance from 0 up to A, you can see that, okay, it is less than the radius. In other words, we have our I on the negative side, but this point A here is still above -1. We haven't reached -1 yet, so it is still above this -1 here, and also it is below 0. So we have a point that is somewhere in between there, right? If I choose my B to be there, I will have a B, and then I draw a line from B to the origin, and I want a point perpendicular to the axis, so I will have that point. So A and B will be in the same point there, and the length between A to O is just -1. So at this point here, we will end up reaching a -1 there. Let me use a different color. And now, if I choose my B to be there, draw the line to B, draw the perpendicular line to the axis, you can see that A is going to be there. And the length of OA is between -1 and 0. So it is between -1 and 0. So it is somewhere there. And if I choose my B to be there, I draw a line there, and the perpendicular, draw a line from B to the origin there, you will find out that that same line is also perpendicular to the axis. So our A is going to be at the origin. So the length between O and A is going to be a 0 there. And if I choose my B to be there, and then I draw a line from the origin to B. I draw a perpendicular line to the horizontal axis. What you actually do here, you'll find out A is at that point. That point, excuse me, that point is between 0 and 1. So the point that we will end up getting here is going to be somewhere there between 0 is the x-axis, and 1 is there. And if I choose now my B to be there, let me use a different color, my B to be there, my A will be at the same position, and now the distance from 0 to A is going to be exactly 1. So we are somewhere there. Now, can I join these points? You will find out that I'm gonna get a smooth and nice curve. Let me use a blue actually. I think a blue will work. I'm gonna get a very smooth curve of this kind here. So this is gonna go like this, and then it's gonna go like that, and then it's gonna go all the way like that. So it's gonna be smooth like this. So it's supposed to start turning here. And of course, if you continue this side, you'll find out that you're gonna have a point there, you're gonna have a point at 0, you're gonna have a point somewhere there, you're gonna have a point at 0, you're gonna have a point there, you're gonna have a point at 0, you're gonna have a point there, and you're gonna have a point somewhere there. So this also is gonna go all the way down to 1, and then start it's not that perfect, but I'm trying. It's gonna be like this. So it's gonna continue that way, it's gonna continue that way, and this is as x keeps changing here, this is a plot of OA. But guess what here? We said our OA is the same as cosine of x. So this plot is f of x is equal to cosine of x. So that's what this thing is all about. And now, how do you end up plotting a sec? I'm just gonna plot sec. Sec. This is sec of x, which is the same. Let me just say f of x is equal to sec of x, which is the same as 1 over cosine of x. Note that cosine of x, we have plotted cosine of x. So if cosine of x is equal to 0, this function is not defined there. So note here, I'm going to use red so that this can be seen. When cosine of x is 0 here, cosine of x is 0 there, cosine of x is 0 there, cosine of x is 0 there. At these points, this function is not defined. So what we're going to do, we're going to try and place a vertical line along a vertical line that is passing through these points. Do it like this, and then another vertical line there. This one is not good looking. I'm gonna say this, I'm gonna start somewhere there. Yeah, because we know that this function is not going to be defined at that point, and then I'm going to draw another vertical line there, because you know that this function is not going to be defined at that point, and then I'm going to draw another vertical line there, and then you will see that this function is not going to be defined at that point, and then I'm going to pick a white there, and then I can say that, okay, I just realized that these, I'm just gonna say, okay, these are just the points whereby this function is not gonna touch that point. It's not gonna touch at all. It's not gonna touch at these points. I'm trying to create here the dotted lines. because I don't want this to be too perfect, but I'm trying. Now that we have that, I want us to analyze. So we have here, I'm gonna use black now. I'm gonna use black. I think black is fine. Want to draw f of x is equal to a sec of x, and we said this is the same as 1 over cosine of x. And if you look into this, this is, if this is not equal to 0 at these points here, this function will be not defined. Hence we drew the vertical dotted lines. Yes. And now if cosine of x is equal to 1 divided by 1 is 1, which means sec x is 1. So whenever cosine of x, which is this point here and that point there and that point there, because cosine of x is 1 at those points, then sec of x is also equal to 1. So we expect these points, at these points, this function to intersect them. When cosine of x is equal to minus 1, 1 divided by minus 1 is minus 1, which means sec of x is also minus 1. So at these points here, these functions are expected to intersect. Now, if I pick a point here, I know that at this point they are equal. And now I pick a point here on the curve that is between the x-axis and 1, which means 1 over 2, for instance. If I take 1 over 2, I say 1 divided by 1 over 2. Of course, you can work it out with your head. How many halves in one loaf? So there are 2 of them. Or you can just say 1 divided by 1 over a 2, which is just 2. So 2 is not below 1, it is above 1. Because 1 is here, then 2 is supposed to be somewhere there. And if I pick a point that is somewhere close to 0, let's say maybe in this curve here, close to 0, 0,01, and if you say 1 divided by that 0,01, you get a very big number, which is 100, which is somewhere up there. So you can see in this point that you will get values that are going that way, but they will never touch this, so it's going to be up there. You can see now that you will get a curve that is passing like this there. So it's going up, but it will never touch this, so it keeps going. Now, if I pick a point somewhere here, which is below 0, but less than, but above minus 1, that value is going to be minus 1 over 2. If I plug here minus 1 over 2, I get 1 divided by 1 over 2. 1 divided by minus 1 over 2, which is minus 2. So minus 2 is somewhere there, right? If I pick this point or the same point, these points have the same output, so I will get a point that is somewhere there. If I pick another point that is close to 0 but negative, I will get minus 100. And minus 100, or if I pick a point here, which is 1 over 4, 1 divided by minus 1 over 4, I will get a 4, which is somewhere, I can say maybe somewhere down there. And also, if I pick a point that is somewhere there, I will get something like this. And this is actually telling you that actually you have a shape that is moving this way. You have a shape that is going that way. You have a shape that is going that way. Right. Have a shape going that way. You can do the same thing here. Pick a point here which is 1 over 2, and 1 over 1 over 2 is going to be 2. So of course, even here, you will end up having something like that. But it's not going to touch there. The same thing here will be the same. The same analysis will be the same. So you're going to get something of this kind. And then here, of course, you're going to end up getting something of this kind. Because it was supposed to start turning like this. So you'll end up having like that. So this is sec of x. Or f of x is equal to sec of x. Now, If you look into this function here, you can see that we have drawn sec of x and cosine cos of x and sec of x on the same set of x's. So looking again into this, you will find out that we have drawn a nice curve. And if you look into this curve here, the blue curve, it is smooth and it is defined everywhere for all values of x. So the domain of cosine of x is just x is an element of real numbers. And if you look into these black curves here, at these points, when x is equal to that point, this function is not defined because it's not supposed to touch. At x is equal to this point, this function is not defined because it's not supposed to touch. At these points, you'll find out that the domain of sec of x is going to be x is an element of real numbers such that x is not equal to, because I don't want this to be equal, x to be equal to that, because this function is not defined, so it's not equal to pi over 2. And then if you look at minus pi over 2, the same thing happens. So I don't want x to be equal to plus or minus pi over 2. And then when we arrive here at 3 pi over 2, this function is not defined. The same thing at minus 3 pi over 2, this function is not defined. So x, I also don't want x to be equal to 3 pi over 2. And then of course this is going to continue. These dots mean that. So that's the domain of these functions. And if you look at this function, cosine of x is going in between minus 1 and 1. It does not exceed 1, but it is defined at 1. So the range of cos of x is x is an element of real numbers such that y is in between 1 and minus 1, but it is also defined at those points. So that's the range of this particular blue curve. And the range of sec of x, you will find out that x is an element of real numbers such that this happens. Let me see what happens. If you look at this curve here, I can draw a box here, a black box. Look within this box. Inside this box, there is no this curve is not there. So this curve is taking all the value that are starting at 1 and all the way up. And this curve is taking all the points that are from -1 all the way down. So we know that as long as we have y, is less than or equal to -1, we will have an output in this black curve. Or if y is bigger than or equal to 1, we will have, when we start here and we go all the way, we will end up having a curve here. So that's what this thing is all about. And then now, this you can rewrite it and just say, oh, y is an element of, remember that this is going all the way from -infinity up until you arrive at -1. 1 is bigger than infinity. And then secondly, 1 is included, so we're going to use these brackets, or is the same as the union. And then here, we are starting at 1, and 1 is included, so we should use the square brackets up to +infinity. +infinity we cannot touch, so we use open brackets. So for -infinity and +infinity, we use open brackets. So you can either write it like this or you can write it like that. It is fine. Now, I want us to look at how we can go about plotting the tan of x. So I think that's actually going to be a pretty good analysis. And then from there, we'll try and plot cot of x. And of course, that one we will use it, we'll actually plot it in a different video so that this video is not that long. And also another thing that you can do, you can say, okay, let me try and plot tan of x and cot of x, and then you check now the solution after plotting these two.